Good morning. I'd like to present you a work in progress that I am doing in collaboration with Amparo Gil and Javier Segura to compute the zeros of reverse generalized Bessel polynomials. Reverse Bessel polynomials have many applications. For example, they appear in electronics and signal processing for filter design. In particular, the poles of the transfer function of a Bessel filter are the zeros of these polynomials. So there is indeed a need of an efficient algorithm to compute these zeros. This algorithm is based on a more general algorithm proposed by Segura that uses a four-order fixed point method to compute the zeros of functions that are solutions of second-order linear differential equations. As it happens to any root finding algorithm, we need to evaluate the function involved in the process, and in this case, we will use its relation with the generalized Laguerre polynomials with negative parameter alpha to evaluate them. So in order to create an algorithm to find the zeros of the reverse Bessel polynomials, we will need an efficient way to evaluate the Laguerre polynomials. So let's see first what are the significant elements of the general root finding algorithm proposed by Segura, and then we will see how they apply to our particular case of the reverse Bessel polynomials. First of all, we need to understand the distribution of the Stokes and anti-Stokes lines of the differential equation that defines our function. This is necessary because they will tell us how the zeros are distributed on the complex plane, and they will tell us as well how can our algorithm advance in the correct direction to compute the zeros. In fact, we know that the zeros will lie along or close to the anti-Stokes lines. So once this qualitative analysis is done, we can make use of the four-order fixed point method T mentioned in the paper of Segura, together with a carefully selected step function h, because once we have found a zero with the method T, we want to escape from its neighborhood, or the fixed point method will converge back to it. So in the case of the reverse generalized Bessel polynomials, the anti-Stokes lines will usually look like this picture. And because we know that the zeros of the reverse Bessel polynomials have negative real part, as said before, they will lie along the anti-Stokes lines. These properties make us think that the zeros will appear along this curve that I marked in red, that is limited by these two turning points that I have marked here with a circle. Another property of the reverse Bessel polynomials is that there is a specular symmetry with respect to the real axis. And we also know that the number of zeros is finite. So it will suffice to find half of the zeros along the curve that I have marked before, and then use the conjugate to find the rest of the zeros. In this case, the best strategy is to start at the half of the curve, to be precise, at the intersection of the anti-Stokes line with the real axis, and we can see here below a formula to find this initial point where we take the negative root of the function v that we see here below. With this starting point, we will use the fixed point method t to find the first root of the function, and then with the step function h, we advance in the direction that we see here to consequently find the next zeros of the function until we reach the turning point that we have marked before above. And as said before, once we find this first half of the zeros, we conjugate them to complete the list of zeros. And then basically the outline of the algorithm looks as follows. We first take as a starting point the negative root of the formula that we have seen before, and then use the fixed point method t to find the first zero of the function. Then we alternate the use of the fixed point method t and the step function h to find the first half of the zeros of our function. And then we finish the process by finding the complex conjugate of the zeros that we have already found. And then with that, we have the complete set of the zeros of the function. Now let's see an example of the use of this algorithm in Maple. The first three lines are used to define the fixed point method t that we see here and the step function h that we have here. If you want to check the formulas for these functions t and h, you can check the paper of Segura that I have mentioned at the beginning of this talk. And then in the next three lines that we see here, we just define the parameters of the polynomial that we see here. We will use n equal to 200 and a equal to minus 100. And then the rest of the instructions are used to find the initial point that we have mentioned in the talk. The formula is here. Then we make some considerations on the stopping criteria of the iterative method. Finally, we alternate the use of the function t and the function h to find the first half of the zeros of the Bessel polynomial. And then in the next line, we find the complex conjugate of the first roots that we have found to complete the process. And well, the last line is just a plot of the zeros of the function. So with that in mind, let's proceed to execute the process and see what we obtain. We see here the preliminary steps, and then here it begins the root finding algorithm. We see that the process is rather quick. We have to consider that we are working on extended precision, so of course it will take more time than if, for example, we work on double precision. And my guess is also that it takes some time to print each of the results of the loop, so it should be rather quicker if we didn't show the results, but well, here they are. Here we find the conjugate of the roots, and finally we see here, well, the plot of the zeros that we have found. To sum up, our objective is to develop an algorithm to find the zeros of these polynomials in double precision. If you clock the time that it took for the maple process that I have shown you before to find the zeros, you'll see that it took almost a minute to find all the roots of the polynomial. But in our experience with similar algorithms that use the fixed point method of Segura, we have seen that it should take far less time to complete the process. So, of course, there is room for improvement. What we have already done is the outline of the algorithm that I have shown in this talk. What we need is an efficient algorithm to evaluate the generalized Laguerre polynomials. Once we have that process, the algorithm to find the zeros of the reverse Bessel polynomials will be automatic. Well, thank you for your time.